carbon compound pyruvate, which will go on into the Krebs cycle and be further oxidized. Okay, so we can see we get phosphate used up, not in the form of ATP. That's the important thing. When we that a reaction occurs there, yes? Yeah? An allosteric site is somewhere else on the enzyme. Okay? Can you juggle? Can you juggle? Yes, you can. Come on. We'll make the juggling easy. We will juggle just with one ball. It's called throwing it in the air and catching it. That's all we need to do. We might make it a bit more difficult in a second. Because we're going to add on. This is an allosteric effector. It affects them. So here is the active site. You can juggle. You can eat. There's your audience. Turn around. Just throw it in. Just throw it in. Some enzymes work better than others. So the control that you want to be able to store glucose is different from the control that you need to make sure glucose is used up. So the first then enzyme that's important from a control point of view then is hexakinase. Another enzyme that's important is phosphofructokinase, phosphofructokinase, and that converts fructose 6-phosphate to fructose 1,6-bisphosphate. So that molecule that we had before with the 2 phosphates sticking out. It's the first irreversible reaction that's unique to glycolysis. So that step's an important one. And that's called the committed step. That's the first step in the pathway that's, if it goes down that, it's committed to glycolysis. ATP allosterically inhibits this enzyme. Why? Why does it make sense that ATP levels, when they're high, that slows down the reaction? There's no need for any more. There's lots of ATP, doesn't need any more. Let's slow down glycolysis. But another allosteric inhibitor is citric acid in the Krebs cycle. So here is glycolysis and all the processes over there, which occurs where in the cell? Whereabouts in the cell? In the cytoplasm. The Krebs cycle that contains citric acid occurs over here in the mitochondria. The question is, how and why does the level of citric acid over here in the Krebs cycle, in the mitochondria, affect the activity of the phosphofructokinase over here in glycolysis, out in the cytoplasm?
Increased pH. Increased pH.
Well, it may be important, but the reason is that the Krebs cycle is a cycle, right? It goes round and round and round. And so you don't need to measure all the level of all these things. Measure the level of one of them, and that is enough to reflect the level of all of them, because they're all going round and round and round. So if you know the level of one of them, and that's the citrate in the Krebs cycle provides intermediates for biosynthesis as well. So there might be lots of energy there, but the level of citrate reflects the level of biosynthetic intermediates. So the cell might want more. Now the cell, if it's making lots of things, it wants more citrate. So that feeds back to glycolysis over here and says, we haven't got enough, make some more. So that will speed it up. So if the level of citrate is low, then the level of glycolysis, the activity of glycolysis, needs to increase to make more citrate. So that's feeding back. If the cell has enough, there's no need for any more, and glycolysis slows down. If it needs more citrate to make new things, it needs to go back to glycolysis and say, make more, get that pathway going. So, phosphofructokinase is important as well, and the final enzyme is pyruvate kinase. So they're the 3 irreversible steps in glycolysis, and they are the control points in glycolysis. What about other sugars? Other sugars are rapidly converted to glycolytic intermediates. For example, glycogen loses glucose in the form of glucose 1-phosphate. Is that in glycolysis? glucose 1-phosphating glycolysis? No, but it needs to be converted into a glycolytic intermediate, converted to glucose 6-phosphate. Fructose is converted to fructose 6-phosphate. So all the sugars are, we saw that pathway was central to a cell. Other sugars feed in as quickly as they can into glycolytic intermediates. But what happens to pyruvate, that end product of glycolysis? We said here was our pyruvate. We've got 2 molecules of it. What happens to that pyruvate? And it depends on the conditions in the cell. It depends whether oxygen is present or not. Under aerobic conditions, so when oxygen is present, the enzyme pyruvate dehydrogenase. What's a dehydrogenase? Clue in the name. Removes hydrogen. And if you've got a hydrogen, H, what have you really got? An H. What's that made of? A proton and an electron. It's an electron. Right? So when you've got a dehydrogenase, it removes hydrogen, not only hydrogen gas, but it removes an H. But you're really talking about the electrons. That's the bit that matters. You've got an H plus an electron, and it's the electron bit that matters. So, under aerobic conditions, pyruvate dehydrogenase converts pyruvate to acetyl-CoA. How many carbons has acetyl-CoA got? 2. There's a 2-carbon fragment. This comes off as carbon dioxide. So there is our acetyl group, carried by what? Acetyl-CoA. So CoA takes this away to where it's needed. The same with the other pyruvate. The carbon comes off. You're going to come in at the back. You're going. I was going to say. Remember. What were we talking about? Let's start all over again. Let's start at the beginning of the lecture again now. The pyruvate is 3 carbon. A carbon comes off as carbon dioxide. Here is the acetyl group taken by another CoA. Let's have these as CoAs. Now we're going to form some acetyl-CoA over there. They're taken off to where they're required. Taken off to the Krebs cycle. And we'll talk about that at a future day. As glycolysis generates 2 molecules of pyruvate, then this generates 2 NADHs. And this goes to the electron transport chain in mitochondria. We've said, we know where that ends up. But under anaerobic conditions, without oxygen, the cells carry out fermentation reactions. And they are converted to other compounds. And they're converted to other compounds because we need to regenerate NAD. We remember before, glycolysis generated NADH. And we said that glycolysis needs NAD to continue, the oxidized form. So, fermentation involves the use of an organic electron on a receptor, in this case pyruvate. So there's our pyruvate again. We're now talking about no oxygen, right? And we need to do something with, bring out the NADH. Right? Here's the NADH, here's the electron that's required. We need to do something to it. And pyruvate is reduced to compounds like ethanol in yeast or lactate in muscles. So the function of fermentation is to regenerate NAD, the oxidized form. Okay? So now we've got NADH with the electrons. We need to make that NAD the oxidized form. So what you want to do is to add that to pyruvate, add the electrons to pyruvate, and then run away quickly because we've now got the NAD. And so the NAD, the oxidized form, which is what we want. So things like ethanol in yeast or lactate in muscles. In you do that. So in humans, here's pyruvate, CH3, C double bond O, COH. We're adding on electrons. We're reducing them. We're reducing the compound when we add on the electron. Could we reduce CH3 anymore?
No.
No. Lactic acid. We've got a COH So we're not surprised that we've got a COH over there as well. The only place that this can work is on that C double bond O. Here, that becomes reduced to CHOH. So there's lactate. So pyrate's converted to lactate in muscles when you go running, when you haven't got oxygen, and the reaction is, the important bit is that C double bond O is converted to that CHOH. In yeast, Saccharomyces, for example, brewing and baking, pyrate, CH3, C double bond O, COH, loses a carbon dioxide. This comes off here as carbon dioxide. This C double bond O becomes, we form this compound acetaldehyde. Then again, we use up NADH to form NAD, and we get the formation of ethanol there. CH3, CH2OH. But again, that C double bond O there has become that COH there. That's the bit where it's reduced. So you produce lactate, yeast produces ethanol. What would happen if you carried out that reaction? You become drunk when you went running. And the faster you ran, the drunker you become. So there might be more joggers around. All you need to do is have a McDonald's, then go for a run. You didn't need to run to the pub. It will put pubs out of business. You go for a run and you become drunk as you went running. Go and read what it says about gluconeogenesis, because we have put, and there is a summary that we need to you can read that. Just to take that point, what I just said, I'm conscious of time, just to take that point I said earlier, but I haven't had a drop. Charlie Schwartz had been a social drinker for years, but in 1945 a nightmare began that was to make medical history. While stationed in Tokyo during World War II, Schwartz suddenly became drunk for no apparent reason. For years thereafter, the episodes continued, bouts of drunkenness and monumental hangovers without so much as a beer. His doctor warned him not to drink because his liver was becoming damaged. In 1964, so 20 years later, he'd had a hangover for 20 years. It doesn't appeal. In 1964, Swart learned of a similar case in Japan. For 25 years, a man had endured social disgrace because of his drunken behaviour. Finally, doctors found a yeast-like fungus, Candida, flourishing in his intestine. The fungus was fermenting carbohydrate to alcohol right in his body. He was a walking brewery. He didn't have to go for a run. He had that yeast in his gut that was taking sugars, and it wasn't him that was converting them to ethanol, it was the yeast in his gut that was converting it to ethanol and making him drunk. Now, if you can control this, if anybody can think of a way of controlling this and turning it on and off, you'll make a fortune. The breweries will be against you, but you will make a fortune. The taxman will probably want some of the costs as well, that's different. Okay, so, brush a bit at the end, read through what's there, take 5 minutes while Linda gets ready, and I'll see you again. Okay.